Today we're going to talk about algorithm analysis. This is one of those topics that sounds kind of dry at first, but in reality, this is one of the foundational ideas in all of computer science. Eventually, once we know how to solve a problem, the next question becomes, okay, but which solution is actually better? If we have multiple algorithms to solve a problem, then what does it mean for one algorithm to be better than another algorithm? Now, the word better can mean a lot of different things. Maybe one algorithm uses less memory, or it's easier to implement, or it's easier to debug, or it's easier to understand. But most of the time, the thing that we care about the most is this: how fast does it run? And more importantly, how does the runtime change as the input gets larger? Because an algorithm that seems fast for, say, 10 elements might completely collapse for 10 million elements. That's the entire point of algorithm analysis. We're trying to mathematically understand how expensive some algorithm is, how well it scales, and whether it remains practical as the problem size grows. Throughout this course, we're generally going to treat faster algorithms as the better algorithm. Now, that's not universally true in every real-world situation, but for theoretical computer scientists, runtime is usually the primary metric that we care about. Algorithm analysis gives us a mathematical way to compare algorithms objectively instead of just simply relying on intuition. This slide is, of course, the decorative slide. It exists to, make the transitions feel dramatic, but we're going to skip right past it. What's interesting or maybe funny is that this entire idea is actually quite old. So Charles Babbage wrote in 1864, and I'll just paraphrase some of the stuff that's here. Whenever any result is sought by its aid, the question will arise, by what course of calculation can these results be arrived by the machine in the shortest time? So remember, Babbage was talking about a mechanical computing machine. This was long before modern computers actually existed. So when he's talking about the shortest time, what he's really talking about is this: how many operations does the machine need? How many mechanical steps are required? And really, how many times do we have to crank this particular machine? And honestly, that's the same question that we're talking about today. Modern computers are just simply very, very fast compared to this machine that you see on the slide. But the computational cost still matters. So let's assume some algorithm takes maybe 10 to the 6th operations, and another algorithm takes 10 to the 15 operations. Eventually, that second one is going to be, it's going to finish, but it's going to be completely impractical. So algorithm analysis is really about understanding computational efficiency. And computer science, in many ways, is about discovering smarter ways to compute different things. In order to analyze algorithms mathematically, we need a model of computation. The model that we're going to use in this class is what we call the word RAM model. The basic idea is this: memory is divided into cells. Each cell stores a fixed size integer consisting of W bits, and we're going to assume that W is greater than or equal to the log base 2 of n, where n is the input size. Under this model, certain operations are considered primitive operations, and what this means is that they each cost 1 unit at a time. So there's many examples of what a primitive operation is. They can include addition or subtraction, logical operators like your ands, your ors, your exclusive ors, reading from memory, writing to memory, indexing some array, maybe following a pointer, maybe things like if statements, while loops, having some conditional branch. So in our mathematical model, accessing an array is going to cost us one time unit, whatever that means. Adding two numbers together is going to cost us one time unit. Checking an if statement is also going to cost us one time unit. Now, obviously, real hardware is going to be more complicated than this. the division instruction does not literally cost the same as the amount of time it is to read some data from memory. But this abstraction is going to work very well because it lets us focus on the structure of the algorithm instead of the details of the particular processor that we're on. So under this word RAM model, runtime is just simply the number of primitive operations that we're using, and memory usage is the number of cells that we're actually using. For almost all of the algorithms that we study, this model is going to work just fine. One of the more natural ways to solve a problem is just simply brute force. So brute force means try everything, generate every possible solution, check whether each one works, and eventually we're going to find an answer. Conceptually, brute force is very simple. The problem is that it usually scales horribly. For many non-trivial problems, brute force is going to take something like 2 to the n, or 3 to the n, or n factorial, or worse. Exponential growth becomes catastrophic very, very quickly. For example, think back to the stable matching problem that we saw in the previous set of notes. If we solve stable matching using brute force, what we could do is this, is we could generate every single possible perfect match. Then we can check whether each one of them is stable. The problem is that's just a permutation generator, and there are n factorial possible matchings. And factorial growth is enormous. Whereas the algorithm that we saw in the previous set of notes, the Gale-Shapley algorithm, solved the problem in n squared time. And that difference is gigantic. So if you think about a very simple number, let's say you have 10. If you have 10 hospitals and 10 students, 10 factorial, nope, that's factorial, is something like 3.6 million different permutations that we'd have to check, whereas 10 squared is just 100. So instead of doing 3.6 million, we just have to do 100 different operations, again, relatively speaking. So one of the major goals of algorithm design is going to be, can we avoid brute force by exploiting rather the structure of the problem? And this is where the most interesting algorithms are going to come from. One of the biggest distinctions in algorithm analysis is the difference between polynomial time and exponential time. So polynomial time algorithms are generally considered efficient, and the intuition behind this is that when the input size doubles, the runtime should only increase by some manageable multiplicative factor. Mathematically, what we can say is this, is that an algorithm's polynomial time, if its runtime rather, can be bounded by a times n to the b, where a is greater than 0 and b is greater than 0. An algorithm is going to be considered efficient if it has a polynomial time algorithm. So examples of polynomial time include n log n squared, n cubed. These grow much more slowly than the exponential functions that you may have seen, like 2 to the n, or 3 to the n, or n factorial. Now, there's an important subtle thing that's happening here. Polynomial time doesn't automatically mean that it's a practical thing. So for example, let's say you have an algorithm that runs in, say, n to the 120. Technically, that's polynomial, but it would be completely useless in practice because once n equals 2, 2 to the 120 is going to be very, very large. Whereas something like n raised to the 1 plus, zero point 0.2 natural log of n, it's technically not polynomial, but it might run a lot faster for every reasonable input size. So the constants do matter, the exponents do matter, and the lower ordered terms do matter. But still, moving down from exponential time to polynomial time is usually considered a massive breakthrough in understanding how a problem works. So polynomial time is going to be our definition of efficient. The main type of analysis that we're going to be using in this course is what we call worst case analysis. So worst case analysis asks this: what is the maximum runtime over all possible inputs of size n? So for any input of size n. Instead of asking what usually happens, we ask what could happen in the worst possible scenario. Now, admittedly, this is a somewhat pessimistic view. It's a very harsh view of algorithms, but worst case analysis gives us very strong guarantees. If I tell you that some algorithm runs in, say, big O of n log n, in the worst case, then you know that it's never going to suddenly become exponentially bad. There are, however, some very important exceptions where worst case analysis doesn't really fully reflect practical performance. A very classic example and a famous example of this is the simplex algorithm for linear programming. The simplex algorithm has exponential worst case runtime. So the thing here on the left has a worst case exponential runtime. But despite that, it's heavily used in practice because the worst case inputs, the really bad ones, they rarely appear. Whereas some of the polynomial time algorithms for linear programming have constants and exponents that are very, very large, that they become impractical. So in practice, constants matter, lower order terms matter, and the input distribution actually matters. Worst case analysis is incredibly useful, but it's really not the entire story. Worst case analysis is not the only way that we can use to study algorithms. There are different types of analysis that exist. One other example here would be probabilistic analysis. So probabilistic analysis is this. Instead of asking about the worst case, probabilistic analysis is going to study the expected behavior on some randomized algorithm. Now, you're probably familiar with a randomized algorithm already. For example, quicksort has a worst case runtime of big O of n squared. If you remember quicksort, what you do is you pick a pivot point and you partition the data into the left side and the right side of the pivot point. Well, if you always choose a bad pivot point, if you always choose the largest element or the smallest element, then all of the rest of the elements are going to end up on one side. And this eventually, degrades into like selection sort, where you end up doing n squared operations. But the expected time of quicksort is actually big O of n log n if you do probabilistic analysis. And in practice, quicksort is usually extremely fast. Another important type of analysis is what we call amortized analysis. So amortized analysis is going to study the average cost across a sequence of operations. A very classic example of amortized analysis is a dynamic array. When an array becomes full, so think about pushing elements onto a stack, and that stack is backed by an array. Well, when your stack has a size of 10 and a capacity of 10, and you try and push the 11th element, what happens? Well, you have to resize. And when you resize it, you have to copy all of the elements over. So that resize operation is a linear time operation, but it happens very infrequently. So when we're thinking about a stack and we're thinking about pushing with a dynamic array, when you average the amount of pushes that you have over many, many operations, push is going to have an amortized constant time cost. There are many other kinds and types of analysis as well. There's average case analysis, there's smooth analysis, there's competitive analysis. There are entire graduate courses that exist rather on these topics. But for this course, we're mostly going to focus on the worst case analysis. So the big picture here is this. Algorithm analysis gives us the mathematical framework for comparing algorithms. Instead of just simply relying on tuition, we're going to analyze runtime, memory usage, scalability, and computational cost. And we're going to analyze algorithms using that word RAM model. We're going to count the number of primitive operations. And most of the time, we're going to focus on worst case runtime. One of the biggest ideas throughout this course is going to be the distinction between polynomial time algorithms and exponential time algorithms. Polynomial time algorithms are generally going to be considered efficient, where exponential time algorithms are usually going to become infeasible very, very quickly. Ultimately, the goal of algorithm design is often this: can we find enough structure in a problem to avoid having to do a brute force? And that question is going to derive a huge amount of what we see in theoretical computer science. Now we're going to transition into one of the more core mathematical tools that is used throughout analysis or algorithm analysis. And that is this idea, the asymptotic order of growth. This is probably something that you've seen before in a discrete math course, but now we're going to apply it rather in a much more practical way. The entire purpose of asymptotic analysis is this: how does an algorithm behave as the input becomes extremely large? Because honestly, for very small inputs, anything is going to work. Even a brute force algorithm is going to work if you have very small inputs. Terrible algorithms can look good when n equals 10, where n is the number of elements that you have in your particular set or list or whatever. The real question is this: what happens when n becomes 1 million or 1 billion or much, much larger than 10? That's where asymptotic analysis is going to become important. We're no longer worrying about tiny implementation details, but rather we're trying to understand the long-term growth of a runtime, the scalability of a runtime, and which parts of a function actually dominate as the input grows. Throughout the rest of this course, we're going to constantly translate algorithms into mathematical functions, and then we'll analyze the growth of those functions. Big O notation. So Big O notation is probably the most famous notation in computer science, and technically Big O is an upper bound. What we're trying to do is we're describing a function using another function that grows at least as fast. In algorithms, this concept becomes incredibly useful because eventually we're going to be mapping algorithm runtime to a mathematical function. So instead of just saying this algorithm takes 32n squared plus 17n plus 1 operations, the example that we see on the bottom here, we're going to summarize that by saying that the important behavior of this algorithm takes big O of n squared, because the n squared term dominates the growth. So formally, what is big O? We say that f of n is big O of g of n if there exists constant c greater than 0 and n naught greater than 0, such that 0 is less than or equal to f of n, which is less than or equal to c times g of n, for all n greater than or equal to this n naught variable. And I'm noticing a typo on the slide here that I'm going to fix. This should be greater than 0. Now this definition rather looks intimidating the first time that you see it, but conceptually it's very simple. What it means is this, is that eventually g of n is going to grow at least as fast as f of n. Now the word eventually is important because n naught, because before n naught, anything can happen, as we can see in this example graph that's on the slide. The functions might cross each other, so here's your f of n, and here's your g of n that looks something like this. Anything to the left of this n naught, I don't really care what happens. It doesn't really matter. One might be temporarily larger, one might be smaller. We don't care. Asymptotic analysis only cares about the behavior for sufficiently large inputs. So once you hit this n naught, then we can start saying something about how this function and this function relate to each other. So the example that we see at the bottom here is this: 32n squared plus 17n plus 1. As n gets very, very large, the constant 1 becomes kind of irrelevant. If you're looking at the growth of this function and how it actually looks, the 1 doesn't really matter. I mean, all you're doing is you're just adding 1, so it becomes irrelevant. The 17n term becomes also relatively small with respect to the 32n squared. If you're looking at how this function grows, the 17n is important, but it's not that important. Right? The term becomes relatively small with respect to the 32n squared. So the 32n squared is the term that dominates everything. And so we say that f of n is big O of n squared. And we notice something that's important here. The 32 disappears. In big O notation, we ignore constant multipliers because constants affect the scale, but they don't affect the long-term growth behavior. So if we're thinking about scale, if we just say y equals x, well, y equals x looks like this. If we say y equals 2x, well, then it kind of looks like this. It affects the scale, but it doesn't affect the growth. The growth of n squared is going to look something like this. The growth is going to just take off. So constants don't affect the long-term growth behavior. The function that we see at the bottom is big O of n squared, but it's also big O of n cubed, and big O of n to the fifth, and big O of 2 to the n, because all of those functions eventually grow faster than n squared. But when people are using big O informally, like we're going to be doing in this course, we're usually looking for the smallest reasonable upper bound. So n squared is the most informative description that we have here. So big O, as sort of a nice summary of this page, big O tells us what growth rate eventually is going to dominate the runtime. Let's do a quick example. So suppose f of n is equal to 3n squared plus 17n log n plus 1000. Which of the following are true? And like I said in the previous set of notes, what I encourage you to do is to pause the video, spend a minute or two trying to figure out which one of these is the answer, and then go ahead and resume the video, and I will give away what the answers are. All right, the question here is, which of these statements are true? Well, what we're going to do is we're going to compare the growth rates. And when we're looking at the growth rates of this function, what term here is dominating the overall function? Well, the 1000 here, sure, it affects the function early, but then as n gets really, really, really big, the 1000 doesn't matter that much. The n log n, the 17n log n that we have here, it will matter, but it doesn't matter as much as the n squared. The n squared will end up dominating this function in the end. So the dominant term here in this function is the 3n squared, because n squared grows faster than n log n. So this function is definitely big O of n squared. But remember, big O only asks for an upper bound. And since n cubed is also going to grow faster than n squared, this is also true. So it turns out C is our answer. Both A and B is correct because both statements are true. And this is one of the common mistakes that I see people make, is that thinking big O is going to give a unique answer. It does not. There are infinitely many valid upper bounds. Once you've found an upper bound, well then multiply that upper bound by n, and now you have a bigger upper bound. And then you multiply that by n, and you have an even bigger upper bound, and so on, and so on. What we are usually going to do is we are usually going to prefer the tightest or the most informative upper bound. Now we need to talk about something that is slightly annoying. Computer scientists, we love to abuse notation all the time, and big O is one of the biggest offenders. So strictly speaking, f of n equaling big O of g of n is not an equality. What we're actually saying is that f of n is an element in some set. So f of n is in this g of n set. What that means is that f of n belongs to a set of functions that's bounded above by g of n. So for example, let's say that you have 5n cubed as one of your functions and 3n squared as another of your functions. Both of these things are equal to big O of n to the cubed. That's what we would say. But obviously 5n cubed is not equal to 3n squared. So Big O doesn't behave like an ordinary equality. You can't freely use transitivity the same way that you would use for algebraic equations. If you say A equals B and B equals C, well, then A equals C. But that is not the case with Big O notation. G1 of n does not equal G2 of n, at least in this example. Another subtle point that we have with Big O notation is the domain. In algorithms, and in this course, our input is usually going to count the number of things that we have. So for instance, the number of vertices, or the number of elements, or the number of edges, or the size of an array, or the number of operations that an algorithm has. So our functions are usually defined on the natural numbers. We generally don't care about what happens when n equals 3.7 because what does that even mean? What does it mean to have 3.7 nodes in a tree? Or you have 3.7 if statements in some algorithm? That doesn't mean a whole lot in this course. So usually n is going to be natural numbers, so non-negative values for n. And we're not going to care too much about what happens when n is a real number. So the bottom line is this. Notation is useful. We're all going to use this, but just be careful not to interpret it kind of too literally. Don't use equality as ordinary equality. So it's okay to abuse notation in this course. Just make sure that you don't misuse the notation. All right. Now let's take a look at some of the algebraic properties of Big O notation. These properties are going to become incredibly useful because they let us analyze algorithms piece by piece instead of having to completely rederive everything from scratch every single time. The first property that we have here is reflexivity. So it's a reflexive thing. A function is always big O of itself. F of n is equal to big O of f of n. F is big O of f. So for example, 3n squared is equal to big O of 3n squared. It's not exactly groundbreaking, but it's mathematically important. The next thing that we have is constants. Constants do not matter asymptotically. So for example, if f of n is equal to big O of g of n, and you have a constant c that's greater than or equal to 0, or greater than 0, rather, then c times f of n is equal to big O of g of n. So this is why 1000 n squared and n squared are considered the same asymptotically. So whether you have n squared, well, this thing is big O of n squared, and 1000 n squared is also big O of n squared. So constants here do not affect the growth rate. Now in practice, of course, constants matter. An algorithm that runs in 1000 n squared is going to be a lot slower than one that runs in n squared time. But asymptotically, they scale the same way. Big O is going to intentionally ignore these constant factors so that we can focus on long-term growth behavior. What about products? So let's take a look at products. This one becomes important for nested loops. So suppose you have, say, f1 of n is equal to big O of g1 of n, and you have like an f2 of n is equal to big O of g2 of n. When you multiply f1 and f2 together, that is big O of g1 times g2. And the proof that you see on the slide here is essentially just algebra. If f1 of n is less than or equal to c1 times g1 of n, which is what we have here, and you have f of 2 of n that's less than or equal to c of 2, g2 of n, then when you multiply both of these inequalities together, what it's going to give you f1 of n times f2 of n is less than or equal to c1 times c2 times g1 of n times g2 of n. So all we do is we update our C value. Instead of C being C1 or C2, we just say, well, C equals C1 times C2. And our N naught now, instead of it just simply being the N that worked for N1 and the N that worked for N2, we're just going to take the largest of the two. So take the largest N1 and N2, and that is your new N naught. Conceptually, this is what happens when you have a nested loop. So this is why we talk about the products here, is whenever we have nested loops, we are going to be using this product property. So for example, let's say that you have an outer loop that runs in n squared times, and you have an inner loop that runs in n cubed time. The total amount of work then becomes n to the fifth. So the runtime for the entire algorithm, if this is what you have as this nested loop, is going to be n to the fifth. So let's talk about sums. This is another property that we're going to use often. Suppose that one chunk of code takes n squared time. So you have an algorithm here, and you have this chunk of code that takes n squared time. And then afterward, you have another chunk that's going to take n log n time. So you have two chunks of code that are separate from each other, where one of them runs in n squared, the other one runs in n log n. The total runtime that is going to be n squared plus n log n. But asymptotically, we don't care about the n squared, or sorry, we don't care about the n log n. The n squared term is going to dominate. So we simplify this to big O of n squared. So that's what this is saying. If f1 is big O of g1 and f2 is big O of g2, then f1 plus f2 is just the max of g1 and g2. We're ignoring those lower ordered terms. The final property that we see here is transitivity. Transitivity is extremely useful. It says something like this. If f of n is big O of g of n, and g of n is big O of h of n, then f of n is big O of h of n. And conceptually, this hopefully is very intuitive. If f of n grows no faster than g of n, and g of n grows no faster than h of n, well, then f of n certainly grows no faster than h of n. As an example, we could look at this. Let's say we have 3n squared. So we have like a 3n squared plus, I don't know, 10. We know that this thing is big O of n squared. We also know that n squared is big O of n cubed. Therefore, by transitivity, we have f of n. So this is our f of n up on top. We have f of n is big O of n to the third. Now, technically, big O of n to the third is going to be a weaker upper bound than big O of n squared, but it's still a valid upper bound. And that's the important thing to remember here, the important thing to take away, is that big O only requires an upper bound. It's not necessarily the tightest upper bound. So these properties are what are going to make the runtime analysis manageable, because eventually we're going to analyze much more complicated algorithms. But all we're going to do is we're going to decompose them into loops, or nested loops, or maybe sequential chunks of code. Maybe we have some recursive calls. Maybe there's some subproblems that get combined. These properties are going to let us combine all of these runtimes together systematically. So runtime analysis is often just repeated applications of most of these few rules that we see on this page. If you understand big O, and if big O makes sense, and if big O is just an upper bound, well then big omega is just the opposite. Big omega is a lower bound. So formally, f of n is omega of g of n. If there exists, so f of n here, omega of g of n, if there exists constants where c is greater than or equal to 0, and you have an n naught, again, this should probably be greater than 0, such that f of n is greater than or equal to c times g of n for all n greater than n naught. And this is exactly what's shown in this graph, just like we had on the previous slide. It doesn't matter what f of n and g of n are doing to the left of n naught. So before this point in time, I don't care what's happening over here. None of this really matters. All that really matters is that um, at some point, f of n is going to grow at least as fast as g of n. So big O says it's no faster than. What big omega is saying is it's no slower than. So as an example, think about this. Let's say you have 32n squared plus 17n plus 1. This thing is omega of n squared because eventually that quadratic term is going to dominate. The 32n squared is the thing that is dominating the growth here. But it's also omega of n. And it's also omega of 1, but it is not omega of n cubed because the n cubed is going to grow faster than that particular function. So in algorithms, lower bounds are extremely important. So for instance, the typical usage that you see in the middle of the slide here is a comparison-based sorting algorithm has a lower bound of n log n. What that means is that no comparison sort, so no sorting algorithm that uses comparisons between two elements can fundamentally beat the n log n growth rate in the worst case. And that's a major theorem that we're going to eventually prove later on in this course. Let's take a look at a small quiz involving some big O notation. And this is actually a very good exercise. So if you haven't been pausing before, I really encourage you to pause this one and think carefully about what the definition of big omega actually is. So pause it for a second and then start it up and we'll go through these. The first statement is this. So the first statement is f of n is omega of g of n if and only if g of n is big O of f of n. And this one is definitely true. I mean, this is essentially the definition of what it means to be omega of something. So f of n is going to be lower bounded by g of n if g of n is big O of f of n. So this statement is true. We're just flipping these functions around. So if f of n is lower bounded by g of n, again, after some point, after some n naught, then g of n is going to be big O of f of n, and that's clearly true. G of n is going to be less than what f of n is. So these are, this first answer is true. And conceptually, again, this makes perfect sense. That's what f of n means. F of n being omega of g of n means f of n grows at least as fast as g of n, and g of n being big O of f of n means g of n grows no faster than f of n. It's really just two ways of saying the exact same thing. Now let's take a look at statement B. Statement B is very subtle, and in our world in algorithms, statement B is basically going to be true because in the algorithms world, as n gets large, your runtime is going to improve. So let's take a look at statement B here. So f of n is omega of g of n if and only if there exists a constant c greater than 0, such that f of n is greater than or equal to c times g of n greater than or equal to 0 for infinitely many n. And this is the problematic thing that we have right here is this infinitely many n. What this is not a strong enough statement. Oh, didn't mean to do that. This is not a strong enough thing to say. Because remember what the actual definition of big omega is. We need f of n to be greater than or equal to c times g of n, and we need that to hold for all sufficiently large n. So all sufficiently large n, meaning every n greater than some n naught, and not just some infinitely many scattered values throughout the function. And these are very different ideas. A function might occasionally spike upward infinitely many times, but it still is going to fail to stay above the bound consistently. So let's say that you have some weird oscillating function that's going to alternate between n squared and 1. And like I said, what the reason that B is true is because of a mathematical issue and not necessarily in an algorithmic sense. Because in an algorithmic sense, this would be weird to happen, where you have a function that is all of a sudden really high, and then it gets really low, and then it gets really high, and then it gets really low, and then really high and really low. When n is getting bigger, essentially what this means is as our input is getting larger, is there going to be a situation where we reach a point where all of a sudden the runtime of our algorithm is just going to drop considerably and get really, really, really fast? And then once we reach a point, it's whoop, now back up here again. That is very unlikely to happen. All right, I can't even think of one off the top of my head. So this won't happen to us very often in this course. But it could happen. All right, this is a technicality that could happen in the math world. So imagine a weird oscillating function that alternates between, say, n squared and 1, depending on whether n is even or odd. This is going to satisfy the inequality an infinite number of times, but it's also going to fail an infinite number of times as well. And that is not going to satisfy the definition of big omega, because big omega is saying at some n naught value, g of n is going to grow slower than f of n. So this is your g of n, and this is your f of n. There has to be a time where f of n grows faster than g of n. But if we're just bouncing back and forth between this, that will never happen. So we do not satisfy the definition of big O with this particular statement. So statement B is technically false. The condition needs to hold for all sufficiently large values of n and not merely infinitely often. So therefore, the best answer here is A. It's not C, and it's certainly not, or not B rather, and certainly not both. This distinction is important in theoretical computer science, but not necessarily going to be very prevalent in this course. If you understand big O as an upper bound, and you understand big omega as a lower bound, what big theta is going to do is it's going to combine these ideas. So big theta is going to combine big O and big omega together, and that's going to give us big theta notation. So big theta means that a function is both upper bounded and lower bounded by the same asymptotic function. So formally, f of n is theta of g of n if you have constants c1 and c0, or c2 rather, greater than 0, and is n naught greater than 0, such that 0 is less than or equal to c1 times g of n, which is less than or equal to f of n, which is less than or equal to c2 times g of n for all n greater than or equal to that n naught. So for all sufficiently large n. Now g of n captures what we call the exact asymptotic growth. It's not just an upper estimate, and it's not just a lower estimate. It's the true dominant growth rate of this function. So for example, merge sort runs in theta of n log n. What this means is that it is never asymptotically worse than n log n, but it's never also asymptotically better than n log n. This is the true growth rate. So as we see in the example on the bottom here, 32n squared plus 17n plus 1. This is theta of n squared because the quadratic term dominates both above and below. As this function gets very, very large with n, the 1 doesn't affect it as much, the 17n doesn't affect it as much. The thing that really matters here is the 32n squared. But as we saw before, the 32 is just a scaling factor, so we can ignore the constant multiplier out front, and we have theta of n squared as the most precise asymptotic description for this particular formula. So another quiz. There are two especially useful ways to think about theta notation. So what are equivalent definitions of big theta notation? So take a look at these examples, and then uh, either of these are true, neither of them are true, or if both of them are true. So A is just simply the first definition that we gave. F of n is theta of g of n if and only if f of n is both big of g of n and omega of g of n simultaneously. This one is 100% correct. Now, this is just the definition of what it means to be big theta. The second interpretation that we have here is using limits, and we're going to see this on the next slide. So if you weren't entirely sure about this one, that's okay. But we're going to see this shortly and sort of give some intuition behind why this one is true. So this one is using limits. What it's saying is that as n goes to infinity, f of n divided by g of n is equal to c. So there's some constant c that's between 0 and infinity, so strictly between 0 and infinity. If this is true, then f of n is equal to theta of g of n. This is a powerful test that we have here for statement B, because what it's saying is that two functions are growing at the same asymptotic rate if this one is true. So the limit of one function to another function, if that equals some constant, what it means is that neither of them completely dominates the other. The ratio between these two functions is going to stabilize to some non-zero finite constant. So for example, let's say you have 32n squared plus 17n plus 1. So let me draw that out, 32n squared. What did I say? 17n, I think, plus 1. That's been the classic example in this set of notes. Divided by n squared. So here are two formulas. One of them is the top, and the other one is the bottom. So are these two things theta of each other? And it turns out the answer is yes. As you take the limit of this, as n approaches infinity, what's going to happen? Well, you can split this up. So let me split this up into 32n squared over n squared plus 17n over n squared plus 1 over n squared. As n goes to infinity, what happens? Well, this is just going to go to 0, because 1 over infinity is, well, just 0. This one has your n's cancel, so you have 17 over n, which still goes to 0. So as n gets very, very large, that term is going to go to 0. Whereas this one, as n goes to infinity, well, it doesn't matter. It's approaching 32. So this ratio between these two functions is going to approach 32 as n goes to infinity. So what this means is that this function is big O of, or theta of the second function. What we see on the next slide then, if it goes there, what we see on the next slide then is that limits give us a very intuitive way of comparing growth rates. And this is one of the nicest connections between calculus and algorithm analysis. Instead of staring at some giant function and trying to guess, which one grows faster, all you really need to do is take the ratio between the two. So you have your two functions, f of n and g of n. Just take the ratio between them as n goes to infinity. So now we're not looking at small inputs anymore. What we're doing is we're saying, as the input gets enormous, which of these functions dominates? So the first proposition that we have here is saying, well, if f of n divided by g of n equals c, so some constant, where c again is between 0 and infinity, then f of n is big theta of g of n. And this makes intuitive sense, we saw on the last slide. If the ratio converges to a constant, a positive constant, then neither function is outgrowing the other. They're essentially growing at the same asymptotic rate. The proof of this is actually fairly elegant. So by the definition of limits, when you have f of n divided by g of n, it's going to get arbitrarily close to this c value. So eventually the ratio is going to be trapped between two constants. And what the slide does is it's saying that you have this c minus epsilon is less than or equal to f of n over g of n, which is less than or equal to this c plus epsilon. And the slide chooses epsilon to be 1/2 times c, which is going to be greater than 0. And what that's going to give us, if you multiply, is just simply going to be 1/2 c times g of n is going to be less than or equal to f of n, which is less than or equal to 3 halves c times g of n for all n greater than or equal to n naught. So by our definition, f of n is a theta of g of n whenever c1 is equal to 1 half c, and whenever c2 is equal to 3 halves c. So all this is doing is it's just simply saying that f of n and g of n, the limit as n approaches infinity, if it equals some constant, well then u are theta of each other. The second proposition is saying this, so the one that we have on the bottom here, if the limit of f of n over 0, then what that means is that g of n is growing strictly faster than f of n because the denominator is dominating the numerator. So eventually f of n becomes very tiny relative to g of n, which means that f of n is equal to big O of g of n, and not f of n is equaling omega of g of n. So f of n is big O of g of n if the limit of f of n divided by g of n goes to 0. As an example, you could see something like this. So let's say that f of n is just equal to n, and g of n is equal to, I don't know, n squared. Then f of n divided by g of n is going to, I shouldn't say equals, it's going to approach 0 as n goes to infinity. So what that means is that n is big O of n squared, and n is not omega of n squared, because linear functions grow much slower than quadratic ones. Finally, the last proposition says this, is if the limit of f of n over g of n equals infinity, then the numerator dominates the denominator. So f of n is growing much faster than g of n. What that means is that f of n is omega of g of n, but it's not big O of g of n. So this slide is important because it gives us a practical technique of trying to figure out whether or not a function is big O or theta of or omega of some other function. Instead of trying to prove the asymptotic bounds directly from some formal definition every single time, you can often compute it just by looking at its limit. And if the limit is 0, well then that tells you one is big O of the other. If it goes to infinity, well that tells you one is omega of the other. Or if it goes to some non-zero constant, well then you know that they are theta of each other. So limits let us compare functions by asking which one dominates as the input size becomes enormous. What we see on this slide is just some asymptotic bounds for some common functions. So let's say that f of n is equal to some constant a0 plus a1 times n plus a2 times n squared plus ad times n to the d. Then this function is theta of n to the d. What we're doing here is we're looking at the largest term, and that is our theta value. It's also our tightest big O value and our tightest omega value. And you can look at the limits of this to see that this is the one that actually matters. So as you divide this by n to the d, you're going to end up with a constant, which is a to the d, where the rest of these are just simply going to go to 0. So the bounds that we saw, or the limits that we saw on the previous page, help us to show that the largest term in some function is the theta term for that function. Logarithms are another common thing that we're going to see. So log a of n is theta of log b of n for every a greater than 1 and b greater than 1, where a and b are constants. And the proof is just simply this, is that when you divide them, what you're going to end up with is a constant. Logarithms with polynomials, so the log base a of n is big O of n to the d for every a greater than 1 and every d greater than 0. And the proof of this is this limit. So the log a of n divided by n to the d is going to equal 0 as n goes to infinity because this term will dominate. the term that's on the top. Exponentials and polynomials look like this. So if you have n to the d, that thing is big O of r to the n for every r greater than 1 and every d greater than 0. So what this means is if you have n to the 20, this thing is big O of 1.1 raised to the nth power. And the proof for this is here. So n to the d divided by r to the n will approach 0. What that means is n to the 20th over 1.1 to the n will eventually approach 0 as as n here goes to infinity. A very common thing that we're going to see, especially if we start talking about permutations, is going to be factorial. So n factorial is 2 raised to the theta of n log n. And we will see this one later on in this course. Up until this point, we mostly talked about runtimes involving a single variable n. But there are going to be some algorithms that are just naturally going to involve multiple parameters, especially when we talk about graph algorithms. So for example, we might have n being the number of vertices, whereas m is the number of edges. So now our runtime becomes a function of two variables. Now it's f of m n. And this introduces an important subtlety. If we don't know how m and n relate to each other, then we can't just simply combine them arbitrarily. So for example, let's say we have something like 32mn squared plus 17mn plus 32n cubed. This simplifies asymptotically to this. It is mn squared, which is this, plus n cubed, which is this. So we can't just simply say that it's one or the other. It's actually both mn squared plus mn cubed. We can't necessarily eliminate either term because maybe m is really, really small. What if m is equal to like 4? If m equals 4, well then it's going to be n squared plus n cubed, and n cubed is going to dominate. Well, what if m is not small? What if it's enormous? What if m is equal to, say, n to the 10th power? Well, if m is equal to n to the 10th power, now all of a sudden m times n squared is going to dominate versus the n cubed, because now you have n rather to the 12th plus n to the 3rd. Well, the n to the 12th is going to dominate. So if m is enormous, well then the left-hand one dominates versus n cubed. The issue is we don't know. So if we don't know how m and n relate to each other, then this is the best answer that we can give, is just m times n squared plus n cubed. Now we could say mn cubed, and that would also be a big O value as well, but it may not be the best big O value that we can give. This becomes important when we talk about graph theory, because graphs, we have m being the number of edges and n being the number of vertices. So for example, we're going to talk about breadth first search, and this thing has a runtime of m plus n, where again, n is the number of nodes and m is the number of edges that we have in our graph. And we have to keep both terms because each of them independently contributes to the runtime. So this is one of the first places where algorithm analysis starts to become more realistic. Real-world problems, rather, are going to sometimes involve multiple interacting input sizes, and we need to be able to account for that.